Alright, let's move on to the second part of the lesson, which is regarding polynomial functions and their graphs. When we graph polynomials in one variable, we note that it tends to turn back and forth. For example, remember that a very simple polynomial might be something like an x squared term, a quadratic, and we know that that's going to just have one, I call this a U-turn, and while something else like an x cubed could have two U-turns in it, and so the number of U-turns, it's not really a very mathematical word, but it's a good way of describing the graph, is usually, and there are some exceptions that we can talk about later on in the unit, but the number of U-turns is usually one less than the degree. So we can see that there's one U-turn here for a quadratic, there's two U-turns here for a cubic. If the leading coefficient, and the leading coefficient is the number in front of the monomial with the highest degree, if the leading coefficient is positive, then the graph will rise at the right. But if the leading coefficient is negative, then the graph will fall at the right, as we're moving sort of from the left to the right. As we're looking in the positive infinity direction, the leading coefficient tells you whether the graph will rise or fall. So an odd polynomial function like x cubed, that's an odd number, we can see that on the left it's falling, on the right it's rising, and so it's got opposite end behavior. While an even polynomial function such as x squared, which rises on the left and rises on the right, has got the same end behavior. So let's describe each polynomial function according to its number of U-turns and its end behavior. And so because this is a cubic equation, where we can see that the degree of the first term is 3, and the degree of the second term is 1, and the degree of the last term is 0, and so the degree of the polynomial is 3, making it a cubic, that's an odd amount, and so we know that the end behavior is going to be opposite, and furthermore, we can see that because it's cubic, we can expect to have two U-turns, and then it will because it's a positive leading coefficient, so it will rise on the right, but because it has to have opposite end behavior, that must mean that it falls as it goes to the left. Alright, the second one, I've got a third degree monomial, a second degree, a first degree, and oh look at the end, it's a fourth degree. And so that's the highest degree. That makes this overall a fourth degree polynomial. And that means that because that's an even number, we can see that the end behavior is going to be the same. With a fourth degree equation then, we can expect to see three U-turns. Because the leading coefficient of that largest term is a positive 1, that means it's going to rise to the right. As we go to the right off the end of the graph, it will be rising. And this time though, because the end behavior is the same due to it being an even degree, it will also rise to the left. And the last one, we've got x to the 2 minus x to the 6. Obviously, this one is the one with the highest degree, so it's a 6th degree equation, but now the leading coefficient is negative, and so that must mean, alright, well first of all we can write down that we're expecting as many as 5 U-turns, and then we can see that it will fall to the right. As we go forward to the right hand side, it will be falling at the end. And because a 6th degree equation is even, then it will have the same end behavior, and the graph will also fall on the left. So if I was going to draw some very quick sketches of these three situations, here we've got a cubic that rises on the right and falls to the left, something like that. Here we've got a 4th degree equation, meaning it will have 3 U-turns, and it rises to the right and rises to the left, maybe something a little bit like that. And this one is a 6th degree equation with a negative leading coefficient, 5 U-turns, falls to the right and falls to the left. So there's the fall on the left. 1 U-turn, 2 U-turns, 3 U-turns, 4 U-turns, 5 U-turns, falls to the right. Okay. Just a sketch. Obviously the graphs do look quite different from these, but this kind of gives us an idea about how the degree of the polynomial and the end behavior look like. Now every polynomial function is continuous. That means that you never have to lift your pencil to draw the graph as you move from left to right if it is a true polynomial function. It has no holes, no jumps in the graph, no asymptotes. You can just trace a smooth curve with your pencil from left to right without lifting it. It will have some things called local and global minima and maxima. And so we better go through that and show you what that means. We also have to worry about checking endpoints if our domain has been restricted, like for example in this example. A polynomial function increases as it goes from a minimum to a maximum. So just imagine a polynomial function going up and down. This is a minimum, isn't it? While this is a maximum. And we might call this the global minimum because it is the lowest point on the entire polynomial. Maybe this is the global maximum because it's the highest point we ever get to. This is called a local maximum. Here's another local maximum because it's higher than the surrounding points. This would be a local minimum. And in fact, every time that you have a global minimum, it's also known as a local minimum because compared to its surrounding points, it is smaller. Similarly, this over here would be both a global and a local maximum. So in fact, every global max or global min is also a local max or local min on a polynomial function. But you could have other local maxes or local mins that are not global themselves. There's only one global max and one global min, but you could have multiple local maxes and local mins. And we can see that as we go from a minimum to a maximum, we must have our function must be increasing. As we go from a maximum to a minimum, we can see that our function must be decreasing. Alright, so the last example. We need to use our graphing calculator to find the coordinates of the minima and maxima in these graphs, and we need to describe the intervals in which each polynomial function is increasing and decreasing. So let's put in our first function of 4x cubed minus 2x plus 1. And we'll graph it. And that's kind of the shape that we expected, isn't it? Because it's a cubic, okay, because it's an odd degree, we did expect the end behavior to be different. Here it's falling on the left, and it's rising on the right because of our positive leading coefficient. Now I'm going to zoom in a little bit. It looks like I don't need all this information with the negative x's or the positive x's, so let's change the window and look only in between, say, -3 and +3, and see what we get now. Alright, we get a much better picture of what's happening. We're supposed to find the coordinates of the minima and the maxima. Well, because this graph does not have a restricted domain, we're assuming that it's going to continue through all the real numbers, and so it's not going to have a global maximum. It's going to keep rising forever, and it will never reach a maximum. Similarly, it's not ever going to have a global minimum. It's never going to reach an ultimate lowest point because it goes on forever. But I do have a local maximum and a local minimum here. And so let's find those. I can say second calculate and go to let's find the minimum first. And so minimum, we want to move our cursor to the left side of where I believe the minimum to be, and then hit enter, and then move the cursor to the right side of the minimum that I can see, and then I can guess by moving the cursor directly on top of it, or as close as I can. Tells me here that the x coordinate at the minimum, so that I should describe this as a local minimum because there are no global ones. Here the local minimum is x 0.408 if I round to 3 significant figures, and a y value is 0.456. So those are the coordinates of the local min. And our local max, similar procedure, except now inside the calculate menu, I'm choosing option 4 for maximum. And instead of moving my cursor to the left and moving my cursor to the right, then moving my cursor to the guess, I can just type in a number that I can see is clearly on the left. Like -1 is on the left of that local max. And then I can see that 0 is on the right of the local max. And it looks to me like it happens at around -0.5. So that's my guess. It tells me that in fact the local max is at -0.408. And the y value looks like it's at 1.54 when I round to 3 significant figures, not 3 decimal places, 3 significant figures. And then we also need to describe the intervals in which the polynomial function is increasing and decreasing. Alright, so first of all, our intervals of increase, we can see that it's increasing all the way here. It's rising. And so everywhere from -infinity up to -0.408. And then also there's another region where it's increasing, everywhere from the local minimum up until, well, forever. So 0.408 up to +infinity. And then I've got interval of decrease in between the maximum and the minimum. So that's going to be everything in between, but not including, of course, because I can't, it's not actually increasing or decreasing at a maximum or a minimum. It's doing neither. All the way up to +0.408 will be the interval of decrease. And last example, let's clear this function and put in our new one. So we've got -2x cubed minus 5x squared plus 6x plus x to the 4. Let's look at the graph. And much like we expected, because of the leading coefficient being positive, it rises on the right. Because it's a 4th degree equation, we can see 1, 2, 3 U-turns. And because it's an even function, the end behavior is the same on each end, meaning it both rises on the right and rises on the left. Alright, a little bit quicker this time. Let's find the coordinates of the minima. I can see that there's this time 2 minima, and I'm not sure right now which one of these is my global minimum and which one is simply a local minimum, but I'll find out in a minute. So second calc minimum. Let's find my left minimum first. So -2 is safely on the left, 0 is safely on the right, and it looks to be at around -1, and in fact it's at -1.3. Well, I can't really tell. Is that a -1.31? Sorry, the resolution of my calculator isn't very good. But it looks like I've got some kind of minimum at -1.31 and a y value of -9. And then we'll do it again, find the other minimum. And the right-hand one, we can see that 1 is safely on the left, 3 is safely on the right, and 2 is pretty close. Turns out that the minimum is 2.30 and a y value again of -9. So because these are both equal, they are both local and global minima. So I guess it is possible, now that I think about it, that you could have 2 global minimum if they are equal to one another. And then we've got to find the max. I don't have a global max because it rises forever. Oh, I just realized I've got a restricted domain, don't I? I'm only going up as high as 2, so this one, in fact, I've got to get rid of because it's outside my domain. So yeah, sorry about that. And then to find the maximum, similar procedure, okay, where you're going to do the left bound and the right bound and the guess, and oh shoot, looks like I've messed up and I'm running out of time. But anyway, we can take this up in class if you've got any questions about this last example.